Hello and good evening to all the viewers on Physics for Students, and welcome to yet another podcast. Since the dawn of physics, gravity has been both our most familiar and our deepest mystery. From Newton's apple to Einstein's curved space-time, every generation has tried to peel back another layer of this invisible force that shapes galaxies and bends light itself. But what if Einstein's general relativity, as elegant as it is not that final word? What if the universe is whispering to us about modified laws of gravity? Well, to explore these questions, we have with us today someone very special who has been listening closely to those whispers, Dr. Bhaswati Mondol. Dr. Bhaswati is currently a Vice Postdoctoral Fellow at the Indian Statistical Institute, Kolkata. She earned her PhD in physics from the Indian Association for the Cultivation of Science, where she dived deep into modified theories of gravity in astrophysical contexts. Her works bridges cosmology and astrophysics and has been published in some of the world's leading journals, including Physical Review D and monthly notices of the Royal Astronomical Society. But her story does not stop at research alone. Dr. Bhaswati has inspired students as assistant professor at Amity University, teaching everything from classical dynamics to relativity and guiding young minds in both undergraduate and postgraduate physics. She has also contributed to advanced teaching at ISES and was recently invited as a resource person at the IUCA's General Relativity Refresher course. We were just talking about some of our wonderful experiences, which we will definitely hear. An honor that speaks to her standing in the field of gravitational physics and cosmology. We are truly honored to have with us today the fascinating world of modified theories of gravity. So let us welcome, in spite of a lot of, I would say, personal and professional commitments, Dr. Bhaswati is there today with us, and a warm welcome to all our viewers and listeners joining this journey through space-time and beyond. Dr. Bhaswati, a warm welcome to today's podcast.
Uh, am I audible clearly?
Yes, absolutely.
Okay. Good evening, everyone. To all the viewers of Physics for Students, it's a wonderful initiative by Shounak, and thanks Shounak for giving me this platform to at least showcase some of my works. Not only the works and why GR has fascinated me from the very beginning of my career. I would say from before bachelor's itself I was very fascinated what is gravity, and I was very strict that I would like to work on gravity. At that point of time I was not very much aware of the research works what was going around, but somehow I had in my mind that I would definitely work, or I would definitely go for this work, because when I was a master student at IT Madras, I was working in quantum communication and quantum computation. Okay, so
Right.
I thought of pursuing my PhD in that domain, but in back of the mind, gravity was hindering me. So
Absolutely.
I was so fascinated about this subject that I left IIT Madras and then I joined ICS as a PhD scholar with Professor Soumitra Sengupta, very well-known person, and he has already
Absolutely.
been in your podcast earlier. I
Yes.
have seen him talking
Right.
about these fascinating topics,
Right.
and then
Absolutely.
I first of all I thought of doing my research in purely theoretical domain of classical as gravity, I would say, because quantum gravity I was generally not preferring for my research topic, because at that point of time, because string theory was kind of obsoleting, because some the research areas were somehow struck in some
Right.
uh, some point. So I thought of doing my research purely in the theoretical aspects. Then some astrophysical works which was observed during that point of time was somehow inspiring me to move further GR and do
Right.
some. research work beyond that GR. So I will
Absolutely.
come to that point. But first
Absolutely.
of all, I would like to start this today's journey
Yes,
from the
yes. So
historical
to the
point of view.
viewers, yeah. So to the viewers, how we would go ahead, because this is a very serious topic. Dr. Bhashatu would be talking. So she has prepared some very good slides. So we are now starting the journey from Newtonian mechanics, and we will take you through a fascinating journey, finding the limitations and why modified gravity is required. So hold on to your seat, and if you have any questions, do let me know. We would prefer to answer the questions last, but yes, viewers are always the first priority. If there are any
Yes,
relevant
absolutely.
questions, please let us know. Dr. Bhashati will be answering. So, but Dr. Bhashati, you can start with the slide. I will just add to the stream and we can go ahead with the journey.
Okay. The slides
Yes,
are visible.
right. We can go ahead. Yeah,
Okay, I'll
please.
just make it to full screen so that it would be really. Ah, yeah.
Yeah, this is fine. Right.
This is fine, right? Okay. So, right now, I just said why GR has fascinated me from the very beginning of my career. So, I will go through deeper into that. But before that, general relativity, it comes to special relativity. Prior to that,
Second,
it
sorry,
was.
sorry to interfere. I just forgot wishing you a very happy Teachers' Day. And Rajkumar
Oh,
Mukherjee right
thank
on the
you.
screen is telling Happy Teachers' Day. Yeah, my mistake. I should have wished all the subscribers and to Dr. Bhashati a very happy Teachers' Day. I think the students are fascinated to get a teacher like you. You are an absolute great
Thank you.
speaker. Yeah, happy
Thank you
Teachers' Day
for
to
this
Rajkumar
respect.
also. Yeah,
Okay,
please go
thank you,
ahead. Sorry.
Rajkumar, for the wish.
Yeah.
Let me go to the journey. So, prior to that, when we were studying in school, what we were knowing about GR? It was just gravity, right? G equals to 9.8 centimeter per second squared. That's all. 9.8 meter per second squared. That's all we knew about GR. What is that? That the gravitational acceleration. We didn't know much beyond that. At least in when I was a school student in HS or before that, we absolutely know this that there is a gravitational constant, and that is a constant value, that is G. But is it really that gravity is only the gravitational constant or gravitational acceleration? It is not, right? Because nowadays, whatever the research work is happening, we can see that GR is much more than this just gravitational acceleration. And also, when we were studying physics in class 10 or class 12 or before that, we used to study only the classical physics. Even at that point of time, we really don't know, or we were not that much aware that what is classical physics, what is quantum physics. These differentiations were not so much clearly known to us. The physics we were studying was just Newton's law. The Newton's law, the three Newton's universal law were taught, and those were the fundamental aspects of physics that we were really fascinated about at that point of time. So I will start from that Newtonian mechanics or Newtonian physics, whatever you can say. From that, I will go how the stages are coming to GR or general relativity, and right now this is modified GR or beyond GR we are also researching about. So first of all, at very preliminary time, Aristotle, a Greek philosopher, laid the main foundations of physics. But we always want to challenge what is there, right? Otherwise, research couldn't happen. So, Galileo was the first person who challenged Aristotle about physics with experiments on motion, and along with Kepler, formulated the empirical laws of planetary motion. But Newton's unified framework was there. That is what I said, that the three laws of motion, and Then he introduced that gravitational law of universal law of gravitation. That is what I told, that the gravitational acceleration was taught about the gravity in those early days of our studies or early days of our career. And that was published in Principia, as we all know, as famous research work about Newton. So, what is the universal law of gravitation? Every particle attracts every other particle with a force. Rather, you will say that it is a negative force. That is also known, that F equals to minus gmm by r square. That's what we have we are taught. We were taught at that point of time, and we used to solve that for different masses, different radius. That problems were coming along, and force proportional to the product of their masses, right? F equals to gm by r square. F is proportional to the masses. That is what universal law of gravitation were taught in that point of time, and that was very clearly explaining the planetary motion and the tides. That is all we have taught in geography as well about this gravitational acceleration. But we can see when we look at beyond our eyes, right? That is in a very atomic or subatomic level. Go beyond that. Practical or everyday applications involve the engineering, essential engineering, space exploration, and technology. But challenges were at high speeds or strong gravitational domain. When we are going at high speed, specifically when we are going beyond the speed of light, we saw that our classical mechanics or the Newtonian physics or those universal law of gravitation seems to fail to explain those aspects. And that is where we need something beyond this Newtonian physics or Newtonian mechanics. So these are the limitations where Newtonian mechanics fail. I have jotted down some of them, but there are much beyond theories involved in this. In a small podcast, we are not able to explain all of this, but I will try to focus on the main points where the Newtonian framework fails.
Actually, just to interfere, Dr. Bhashati, when you're
Yes.
talking about Principia Mathematica, just one fascinating theory came in, a fact came into my mind. Newton, when was not actually willing to publish Principia Mathematica, because before that Galileo was taken in custody, etc.
Right.
So one day Edmund Halley visited Newton's
Yes.
house, and he told him that,
Yes, yes,
see,
yes.
these are the Newton's
So
laws of motion.
in that time as well, we can see when
Yeah.
we can see that anything happening. Hello. Uh, is it audible?
Yes, yes, it is audible. Sometimes it is
It
streaming,
is
but
audible.
you can. Yeah, yeah.
Okay, okay, okay. Fine, fine, fine. This is right.
Uh, no, your screen is not showing
To
right
go.
now. Just a second.
Just give me a moment.
Yeah, sure. Little bit of network
So
issue, but
even back then, it was
yeah, yeah,
very clearly seen. It was very clearly seen that whenever you challenge the notion of whatever is going on, or you are against the flow, something lawful action was taken even at that point of time. So it is
yes,
very
absolutely.
common these days in. Yes, so now it is showing correctly, right? The slides is coming fine.
Yeah, yeah, it is coming. So, yeah.
Okay, okay, I'll just go on. Okay. So I have discussed that Newtonian mechanics was very perfect explaining the regular or everyday actions or everyday motions at and also the gravity at ordinary scales, because that was because our everyday activities are not at the speed of light. So there Newtonian mechanics was very successful. But it fails to describe phenomena at high speeds, very small scales, or in extremely strong gravitational fields. These limitations led to the development of modern physics framework, which includes the GR. So, when we are going beyond that speed of light or at extreme high speeds, what is the main thing it's hindering us to explain the classical domain or the everyday activities? So we have assumed in Newtonian's framework that the time and space is absolute. So the Galilean transformation was x prime equals to x minus vt. So if you are going from one inertial frame to another inertial frame, it's just a difference between those two frames. If the frame is moving at a constant speed v, so then the equation was that x prime equals to x minus vt, and the other components were remaining absolutely intact. That is y prime equals y, z prime equals z, t prime equals to t. That was the equation of state between these two inertial frames, if s is a one frame and s prime is another frame. But when we are going very close to the speed of light, predictions deviate from experiments. That was encoded in Einstein's special relativity, which was the celebrated uh, special relativity at 1905, which introduced time dilation, length contraction, and mass energy equivalence. What are these? I will come to that. So it has, I have already discussed this, so I am just skipping this slide. So now when we are seeing that when we are close to speed of light or even going beyond or at even very small scale, the Newtonian mechanics is failing. Why? So that I just now spoke that the equation between the two inertial frames was just the Galilean transformations. But the problem was we were taking space and time to be absolute. That was the first problem which was discussed or discovered by Einstein. He said that there is a problem when we are speaking about absolute time and space. That should not be the case. The relation between those two frames should be somewhat changed by that point that this is going beyond the speed of light, and he invented this Lorentz transformation, the famous Lorentz transformation, and the equations are already in the screen, and these are the time dilation and famous length contraction which replaces Galilean transformation and results in decrease of the speed of light. These are already verified in some daily experiments like muon decay experiments and high speed particle physics. And these guys often affirms that time and space are all relative. So these basically is important in some modern physics technologies, that is GPS technology, particle accelerators, and this is the most important part of the modern astrophysics and cosmology. Now, we when some observations are happening in and around our universe, we see that this special relativity are also failing in some part of the observations. So previously we saw that the Newtonian mechanics was failing or Newtonian physics was failing in when we are going to the close to speed of light or even at a very small scale. It was not able to explaining those areas very clearly, and why that was happening, because we were assuming that the time and space are absolute. But in special relativity, we have cal- uh, incorporated that relativeness of space and time, right? But why this is failing? That is seeing that when SR or special relativity is formulated on flat Minkowski space-time, there Lorentz transformation holds true. Now, what is Minkowski space-time? When the background is flat, There is no curvature. We are just on a like a straight line you can imagine of. In 2D domain, you can just think of a straight line that is a 2D plane. There the Minkowski spacetime, and that is called the Minkowski spacetime, and there Lorentz transformation holds absolutely fine, and special relativity is very celebrated there, and very well successfully describing those phenomena in that flat background. But it has a crucial or tricky point that we are seeing only inertial observers at constant velocity. But if you can think that inertial observers are not very realistic, right? That is very optimistic or very theoretical point of view. In general day or in our universe, non-inertial observers are there. Non-inertial observers are most realistic rather than the inertial observers. So there, the special relativity fails to explain the observational point of view, and the special relativity have that limitations in that point. So the exclusion of the special relativity is the accelerated frames, gravitational fields, because nowadays all, if we are all aware of that, the we are seeing that Big Bang expansion, the uh, background is accelerating, we are saying that universe is expanding. So that is not an inertial point of view, we are going beyond that, and that are non-inertial frame of reference, and their special relativity fails to explain those. So gravity manifests as acceleration, that is already I have mentioned, but special relativity lacks a mechanism for universal interaction of mass energy. There is no curvature. We are seeing that there is a flat space-time, and that is called the Minkowski space-time, and that is denoted by the Minkowski metric, that is eta mu nu. And now, if we are talking about metric, what is that metric? And what is that eta mu nu? When we were seeing the Newtonian physics, we were only considering that vector, right? X bar, or t was not a vector, t was a scalar, time is scalar, and x or x y z, if you were taking about the three dimension, and t as the fourth dimension, so we were constraining that x vector and t. But now, when SR was invented and Lorentz transformation was invented, we incorporated all the space elements and time elements into a called four vector. That was a three-dimensional x, y, z coming into a three-dimensional vector. But now it is going beyond. We are incorporated the time as well, because we have seen that time is no more absolute, so it is also relative. So we are taking into account as a four vector, the space component is there and the t component is there. Now
Okay,
when we are
I
talking,
just have a question, Dr. Bhashati.
yes,
This
yes,
eta mu nu is a convention which is followed in special relativity, and g mu nu is a convention which is followed in general relativity.
general relativity, G mu nu. Because,
Okay.
very good question, eta mu nu is for flat space time. Eta mu nu doesn't account the curvature or the curved space time. When we are dealing with gravity, or when we are going beyond special relativity and entering into the general relativity domain, we can see that eta mu nu does not hold, because there the space time may be flat, may not be flat, that can be curved, and that cannot be counted in the eta mu nu. Eta mu nu is the flat background metric, and G mu nu is the curved background metric. You can write G mu nu as eta mu nu plus some perturbation like H mu nu. That you can write.
Yeah.
But the
And
flat part is there and the perturbative part is there, which accounts together as the zeta mu nu. That is the
right.
metric tensor. Yeah,
One
tell
more
me.
question. The light
Yes.
cone that we see in special relativity, the Minkowski spacetime, that light cone shape is coming out of the hyperbolic geometry.
Yes, right.
Yeah, you
Any
can
more
go ahead.
questions?
No,
Okay.
correct. Yeah.
Okay, fine. So where was I? Yeah, when flat spacetime was explaining, eta mu was doing fine, because that accounts for only the four vectors in a flat spacetime. But These special relativity cannot explain bending of light by gravity, gravitational time dilation, perihelion precession of Mercury. These are the very famous observational aspects, and we see that special relativistic formulations or the equations of special relativity, that Lorentz transformation, does not hold here, and the theoretical and the observational results are definitely giving very far from each other. And then we thought that there is some mistake and we need to go beyond special relativity. So one important aspect is here in GR, that local equivalence between uniform acceleration and gravity. So you can thought of experiment, that thought experiment was very earlierly told in our high school days, but that was not very clear at that point of time. But you can see that when we are dealing with GR or going into the four vector. Oh, yeah, I forgot to mention that four vector. Yeah. So when we are going to four vector, there comes the concept of tensor that I will explain in detail in my next few slides. Just hold on for a minute. I'll just give the brief glimpse what is that tensor is. That accounts for the three vectors, four vectors, and much beyond that. So when you are seeing the five-dimensional things or 10-dimensional things, you cannot explain those with only the vectors. That is the three-vector, three-dimension quantity. So you have to go beyond, and the tensor gives the higher dimensional quantities, and it is giving flawlessly all the ideas, and these are incorporating the scalars as well as the vectors and beyond. So rank 1 or rank 0 tensor is a scalar, rank 1 tensor is a vector, rank 2 and beyond that is the tensorial part, and that is necessary when we are going beyond that four dimension or three dimension. We are just thinking of three dimensional in our daily life, but now we can just see that when we are incorporating time as in the vectorial domain or in the tensorial domain, that x and t are coming clubbing together, then we obviously need something, some mathematical quantity which is beyond that vector, and that is the tensor. So metric is where we were dealing with, and that is a tensorial quantity. That eta mu nu is obviously a tensor. Now, these are all we have already discussed, that non-inertial frames requires this physics, and SR fails to explain the non-inertial domain physics, and we need to generalize this special relativity to include arbitrary coordinates and curvature. That's what where eta mu nu will fail, because we need to incorporate g mu nu, where the flat, you can just think of the curved spacetime as a flat spacetime with some perturbative area to incorporate the curvature of the spacetime. So here you can
Dr.
see that,
Mashadi, this is the
yes,
equivalence principle that you told. Reminds me, I think Einstein called it the happiest moment in his life at the Bern office when he thought that if the floor collapses and if you fall,
yes,
then that is basically called the happiest moment in his life.
yes, 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 that the
1905.
free fall
Free fall,
experiment. Yes,
absolutely.
yes, yes, yes.
Absolutely. And I will tell you one more thing just to experience, because my college is located on the 14th floor. And each day in the
Okay.
morning at 8:30 or 9 o'clock, when I'm pushing up my elevator, every day I remember and I think that this is actually when the elevator is pushing, you feel the gravitational force and the same force you feel when you're standing on the floor. And today on 2025, we can think of this when we are climbing up an elevator. But in 1905, how
Yes,
Einstein thought that, it is really amazing.
remarkable. Yes, yes.
Absolutely.
Just listening to you, I just remember when I was in school days, and I have read about this free fall thought experiment. That was that time called that thought experiment. And I, whenever I used a lift or anywhere in places, I used to think that this is a free fall only. And I was thinking, so this is happening about that G, that gravitational acceleration. That
Absolutely,
point of time, it
absolutely,
was not known what is gravity. That's what I previously told you, that
absolutely,
at that
absolutely.
point of time there was no notion of such thing. But just thinking of that thought experiment, I was thinking that this is because of that
This is
G, and
because
this is
of
the
the
free fall
G.
only. Yes,
Absolutely, absolutely.
yes,
And
yes.
in Germany, it's called, in German language, they call it as Gedanken, G-E-D-N. Gedanken means actually thought experiment. I read the original Einstein's paper, knowing a little bit of German. So I found that Gedanken, he used that word. That is called,
Okay.
anyway, sorry to interfere. Please go
No, no,
ahead.
no, that is fine because I didn't know this Jedan thing, but thanks
Yeah,
for.
Gedanken is basically a thought experiment. Even this is used by German philosophers like Kant, etc. When you think really something which you cannot experiment, given the restrictions of that generation and time, they used to do this. And Einstein, most important thing, that office in cloud, because my one of my relatives, he visited the school, sorry, the building of Swissborn office. He sent me photographs. Einstein tells that it is very cloistered. I mean to say, a lot of people coming, a lot of business, very disturbed office. And that
Yes,
is
yes.
why I even tell to my daughter and my students that, see, busyness and disturbance actually cannot move you out from the talent. In spite
Right.
of that busy people coming, noises, sounds, etc., he can think. So when you are thinking, outside things actually really doesn't matter. How much
Yes,
sound, how much
absolutely.
disturbance are there. So sitting in that kind of a small office, and he had a very small chair and a table. I went through that pictures, etc. It's a very small place. I mean, it's a very difficult to work with a small table and a chair and a pen and a paper. Even there, if you could think, today we have AC offices and beautiful tables and
Yes,
chairs, but
yes.
still it is a privilege for us. So
Yeah,
anyway, yeah, please.
obviously.
Yeah,
Listening to you, I just one thing I just remind of that Ayuka trip. Recently, I
right.
was in Ayuka. That, as you have already mentioned in the
Yeah, yeah,
introduction,
yeah, yeah.
there I saw that Newton statue, and it was very nice that there was a apple in front of Newton statue. So I was like, is this a real apple fall from it? So it was not. So it was the statue itself, and in memory of Newton. And I came to know that that gigantic statue is only there in Ayuka. In apart from
Okay,
that Cambridge, none other than Ayuka have established that. It's
okay.
nowhere except these two places. And also,
Oh,
I
okay.
yes, and also I saw an apple tree there. So I inquisitively I just asked one of the organizers that, is it that apple tree? I was just jokingly asked them, and they were like, yes, yes, it is an apple tree from that seed. I said, really? Is it true? They were said, yes. There is an apple tree in that lawn, very very small, but that was from that apple tree, that historic apple
Oh,
tree, that seed they
from
have
Newton's
planted.
place.
Yes,
Okay,
yes,
okay. Full
they have
stop.
planted
Okay,
it here,
that's great.
and it is there. So I was really fascinated about this. I was
Yeah, yeah.
standing in
Absolutely.
front that
I
in
saw
front
your
of
picture which you sent me. I saw your picture
yes, yes.
standing beside that apple tree, and this is really a different kind of a feeling. Yeah,
Seriously, I
please go
was
ahead.
so
Yeah,
fascinated because we have learned this, or we have just theoretically saw this, or we have seen pictures from very early days. All we were fascinated about this, that experiment and the theory you have discovered in that time, and seeing that apple tree, it was very like giving me goosebumps at that point of time. So
absolutely.
anyway, going ahead. So as Shonok has pointed out earlier, that eta mu nu is for SR and GR is defined with G mu nu. Yes, eta mu nu is for flat space time, and when we are going to very general case, or the mm, going to the general relativity, it is replaced by G mu nu, and in flat space time, that is just replace eta mu nu with G mu nu, which encodes the curvature of the space time. And these are already mentioned in previous slides. So in summary, we can see that special relativity is powerful for flat space-time, but not for the inertial, non-inertial cases or the curved space-time. It fails to explain there. So these are the limitations: no acceleration or curved trajectories, or no universal interaction of mass energy, no curvature of space-time. But gravity demands dynamic space-time geometry, and ASR cannot explain gravity in that point of time or in this aspect. So we need to go beyond special relativity. Just give me a moment. Yeah. So I have make this slide intentionally to focus on the curvature of space-time, and we have seen many experiments in many science programs or even conferences, that if you just hold on a towel or a handkerchief and just throw a ball on it, you can see that this is going beyond. So the space-time, if you are thinking of that handkerchief or that plane of paper, if you are thinking of that space time, that is getting curved, this is no more flat. So if you put some mass on a space time, or you can just in 2D domain, you can just think of a paper that is a 2D and it is getting curved. So you can see that there SR will fail to explain with the observational aspects, and we need to go beyond special relativity, which is our celebrated general relativity. So I will go through some mathematical formulations with tensors. I have mentioned already about tensors, that is incorporating that 4 vector and beyond, but I will give a little bit of glimpses with some of the equations so that it will be clear to. I know many of your viewers are very much aware of these facts, but as this is a foundations of general relativity, I thought of giving a brief glimpses about this mathematical toolkit. So, as I have said that when we were in school days, that gravity was just a force, that minus F by r, F equals to minus gmm by r square, g was the gravitational constant, but curvature of space time, that is the reality. So gravity is giving the curvature, that the ball is going down when our mass is putting on the space time, this is getting curved. Gravity is playing into role in that point of time. So mass energy tells space-time how to curve, but the space-time curvature tells matter how to move. So now, if you are putting a mass on a space-time, this is getting curved. So mass energy is telling you the space-time how to curve, but this curvature tells how the matter will move on the space-time. So the slide, this is, so if you are putting that ball into that space, this is getting curved, but this curvature will will tell us that how this ball or this mass will move in this space time. So there remains the fascinating aspects of general relativity. So the motion of particles are here described by the geodesics in curved spacetime. I will give a little glimpse of what is geodesy and how that is written. If I have a pen and paper, I could have derived it for you, but as I don't have that opportunity, I'll just go through a slide. Now, as I was having a chat before this interview with Shounak, I was telling that before going to tensors, before going to geodesics, I should remind every viewers that going further into the details, parallel transport is a very important topic where we are dealing with the curved space-time. So what is parallel transport? So parallel transport is a way of moving a vector along a curve. So if you are putting a mass on a space-time, I said the space-time curvature will dictate you how that mass will go around or move in that space time. So parallel transport is the way where how to move a vector or a tensor along a curve in a space time. such that it remains parallel according to the geometry of the spacetime. Now, in flat spacetime, when we are taking that eta mu nu thing, parallel transport is very trivial because there the curvature is zero. If you slide a vector without just rotating, it will remain the same everywhere. But when you are entering into curved spaces, what parallel exactly means? It is defined by a connection known as Levi-Civita connection, or you can say it the Christoffel connection. The Christoffel connection, I will give a glimpse at my next slide. So, a vector transported along a curve keeps the same orientation relative to the space's curvature. That is the parallel transport in general relativity or in curved space-time. So, the parallel transport tells us the how to the vectors will move, or um, the mass will move in the curved space-time, and that is expressed mathematically using the covariant derivative. What is covariant derivative? So covariant derivative, when we just go through the Newtonian physics or classical domain, the normal derivative or the partial derivative is sufficient because their curvature is zero. But when we are entering into the curved space-time, we have to take into account that connection, that parallel transport. How will you incorporate that? That will come through that Levi-Civita connection, and the normal derivative plus that connection term that is in togetherly termed as covariant derivatives. That is the equation gives you dv mu nu d lambda is 0, where the vector v mu nu is parallelly transported along a curve parameterized by lambda. So here you can see that mathematical formulation is also changing, or it's incorporating that parallel transport or that curvature things into account by this covariant derivative. This metric tensor already I have spoken into that.
I
Shounak,
have
I
just
think this sentence is giving you the perfect answer. When
absolutely. I
flat
have just
space
one,
time
yeah,
is
one
your
question.
g mu is equal to
Yeah.
eta mu. Yeah, tell me.
Yeah, I have just one question. Now, when we're talking of parallel transport, we take a globe and we try to keep the vector as early as possible, and then we go around and we see then when it is coming back and the original vector, there is a gap. That means there is the curvature that we are talking about is basically a kind of a curved surface. If it overlaps with another vector, that means that the space is flat. Now, my question to you, Professor, is that parallel transport
Right.
is one of the way in which we are measuring the curvature. In case of we are using
Right.
the Ricci curvature tensor of Einstein field equation, the first element R mu nu. There also we are mentioning the Ricci,
Wait, wait,
curvature.
wait. Ricky tensor. You are wait. Ricky tensor. You are speaking about
Yes, yes,
Ricky tensor. Yeah. The first is Riemann tensor. That is the
right.
fourth order tensor, and then if you just contract with G mu nu, it is giving you the Ricky tensor. Yeah. Tell me, what is the question? Hello.
So in that case, parallel
Hmm.
transport is measuring how a surface is curved. Ricci curvature tensor is measuring how a ball deviates when you move along a geodesics, how the ball deviates from a flat Euclidean space. Am I right? If you can just throw some light on this. I mean, to say parallel transport and Ricci curvature tensor, what is
Yes. Yes.
actually
Right. Absolutely right.
okay?
So, Ricci curvature, basically Ricci tensor does not exactly signify the thing when you have the curved space-time. So, the first thing you need to calculate is that Riemann tensor from that. If you have this Christoffel connection, first you have to first you need to describe your background space-time with that metric tensor. That is your G mu nu. With the help of that metric tensor, you need to calculate the Christoffel connections or that parallel transport connections. That is your gamma mu nu lambda, suppose. So, this gamma will take into account your parallel transport. Okay. So, the parallel transport is taken into account. Now, with the help of this G mu nu and gamma mu nu lambda, you are calculating that what is called Riemann tensor, that R mu nu alpha beta. With that, Contracting with the metric tensor, you are getting that R mu. What is your Ricci tensor? Again, one another contraction with your Ricci tensor with the metric tensor G mu nu, you are getting that Ricci scalar, which is a scalar quantity and the measurement of the curvature of the spacetime. So basically, how the spacetime is curved by what amount or by what quantity, it's just not a number, it can be a function that gives the that is given by the Ricci scalar, and the parallel transport is taking into account or it's absorbed in this Levi-Civita connection. So how
Okay,
that
okay,
two curves going in a sphere, going on a sphere or in a curved space-time, the deviation between these two curves are given by the parallel transport, and that is taken into
okay,
account by that will not take into account the curvature part or the how the space is curved, and to incorporate that as well and to blend it in single form. If you just see the basic social metric that 1 minus 2 gm by r c square dt square plus 1 by fr dr square plus that thing, you can see that there the singularity has been removed by that 2gm by r square c factor. If 1 minus 2gm by r square was not the thing, if only r square was the thing or anything by r and r tending to 0, that theory will fail. We handle these singularities when we are going beyond GR. One is singularity, one is dark matter and dark energy and quantum effects. Till now, what we were dealing with that were all classical. If that we are going beyond that classical domain and that Schrodinger equation comes into place, that the quantum effects turn into place, we see or the observation shows that GR fails to explain those areas. So, what are the singularities? Points where curvature of spacetime becomes infinite. That is what I was telling. If there was a 1 by r factor or more than that factor, r going to 0, that thing explodes, right? And the it becomes infinite, and that is a problem. We need to incorporate or we need to address these singularities. And to address this, the alternative theories of gravity was formulated. Such examples, the best example is the black hole, Big Bang, where GR breaks down and cannot describe the physics inside singularities. So, the notion of black hole is when we are going in the speed of light or much more than that, matter just trapped in that curvature, and there is no way out to coming out from that curvature point of time, that curvature from for that moment. So that is the notion of black hole, and Big Bang is already celebrated. So in that domain, GR fails to explain. So what is dark matter?
okay. Dr. Bhashadi, we have one question. Can we take it up quickly if you don't mind?
Sure, sure.
The question is that, Madam, does GR fails or successful in Sir Roger Penrose's CCC model?
I am not quite sure about the CCC model because I am not familiar with that. I can look into that and let you know if Shounak
Sure,
allows
sure,
me.
no
I can
problem.
just
Yeah,
write it down and you can
absolutely.
just share with them. Okay. So
Absolutely, no
right
problem.
now I am unable to answer your this question because I am not very much familiar with that
Sure,
CCC model.
sure.
Okay.
No problem, no
Yeah.
problem.
Yeah.
Yeah.
So, so what is dark matter? So, GR plus visible matter cannot explain galactic rotation curves. So, there has to be some unseen thing to taken into account for the missing mass. So, the invisible form of matter does not emit, absorb, or reflect light. That is your black hole. That is our notion that if a matter goes into that, it will be trapped and it cannot escape from that uh, curvature, and it will be trapped in there and the black hole forms. So, invisible form of matter that does not emit, absorb, or reflect light and detected indirectly through its gravitational effect. So, if it is trapped and it is forming a black hole, you can hear some noise, or you can get some frequencies, that is your gravitational wave frequencies, which are already detected, and your black hole has already been detected by through its shadow. The exact black hole has not been observed, the shadow has been observed. So indirect uh, observations has already been discovered, and we are dealing with the theoretical part to address that observational aspect very accurately. So the research is going on still. So, what is the evidence of for dark matter? So, I have already discussed that galactic rotation curves where stars move faster than expected, gravitational lensing where light bends stronger than the visible matter predicts, CMB background, that cosmic microwave background where it requires extra mass, large scale structures. These are the Shounak, this is your answer, that where we can use this alternative gravity or the GR where fails. These are the strong domain of research which you can, or which are already been developing very fast these days, but still there is very more areas to be discovered in our near future. So these are the very strong domain where you can use the alternative form of GR, and you can do your research work in these domains. So, which are the candidates for dark matter? Weakly iterating massive particles, actions, sterile neutrons, massive compact hollow objects, and there are so more. I have counted or jotted down a few of them, but there are so more. You can work in these domain as well. And what is the dark energy? These are the dark matter candidates I have just now discussed. And what is dark energy? So, understanding the mysterious force driving cosmic acceleration is the dark energy. So, this forms the energy that makes up about 68% of the universe. So, you can clearly see why beyond GR is necessary. You can see that 68% of the universe is still unknown. You have to figure it out. So you have some observational aspects which are indicating that you need to go beyond GR, because 68% is majority of the universe, right? So if you have to take into account these unknown or the hidden part of the universe, you need to invoke or incorporate this dark matter or dark energy concept. So observations already show that at expanding universe is expanding at an accelerated rate. Again, this is a non-inertial frame of reference. Why we need to go beyond GR now? GR needs a cosmological constant or dark energy to explain. Origin and nature of dark energy remain mysterious till date. So this is a highly recommended domain which the research areas or the upcoming research work is developing, and you can work in this domain, and that will be very fascinating for the upcoming future. And also there are very new data are uh, getting these days. GW's data are almost it's some recent data already have published. You can just work on those to incorporate the modified GR theories there and check whether and how the theory or your modeling is helping out to explain that domain of observational aspects. So these you can go ahead. So, what are the evidence we have already observed in for dark energy? So, type 1a supernovae already have been observed. These are the evidence of dark energy. CMB already I have discussed, and BOW, that baryon acoustic oscillation data, that is already available, that is publicly available. You can just take one BOW data and fit your one beyond GR framework to account for these evidences already upcoming in the observational aspect. And what are the possible explanations? That cosmological constant is playing some role to encounter this. Quintessence model, modifications of general relativity, still an open question in modern cosmology. So this is also a fascinating domain of research these days. Now, what is the importance of cosmology? Shapes the fate of the universe, challenges our understanding of fundamental physics, and drives research in theoretical physics and astrophysics. Also, the quantum effects, we have mentioned that where the GR fails, one was singularity, one was dark matter, one was dark energy, and one was quantum effects. So, GR is a classical theory, does not include quantum mechanics. When you are going into the quantum realm or that subatomic or that level, there the GR fails and cannot describe the physics at Planck scale. So, we need more compact theory to encounter all these things. To resolve these things, we are going beyond GR. And current research work is aiming to unify the quantum mechanics and gravity into a single framework. That is your GUT, right? Grand Unification Theory. That is the most fascinating subject in this era, or fascinating domain of research in this era.
Okay, Dr. Bhashati, we have few
Yes.
questions coming up. I think you are left with just few slides. So shall we wait and then take up the questions? That will be better.
Yes, yes. I think I have two more slides, so I'll just
Yeah,
finish it up
yeah.
and we can
So
just.
yeah, so regular shots, Gunur Singh and NPYOTR and astrophysics. Just wait, we are almost about to end this slide. Yeah, yeah.
Okay, okay, okay. So, so these are the examples of modified gravities. Modified Newtonian dynamics, FR gravity, string theory, loop quantum gravity. You can choose any of these and work on this area to check how the alternative gravities are falling into place. So, here I will end up my slides. But one thing I need to focus on my research areas, because why I have chosen this topic for this podcast, that I myself work in this alternative gravity theories or modified gravity theories. I have worked with FR gravity. I have worked with Bardeen gravity. So the background space-time is modified with some respect, and that is how that extra factor is incorporated with the observational aspects, because we have the observational data. So I have in my PhD time I have worked with the quasar data, that is the observational data we have. But how different modifications of GR is giving the accurate or more or less accurate observational results, that was my primary PhD work. But right now, I'm working in this modified gravity domain as well, but in the framework of astrophysics and cosmology blending. So, in what we are doing in cosmology, so if you are modifying the space time, or you are using that modified gravity, you can check how the Hubble tension or the Hubble parameter is significantly deviated in your theory. Maybe it what is the today's Hubble constant and you are getting from your theoretical point of view is somewhere deviating, and you can check that that extra factor which is present in your space time may be the reason of that deviation. So this is the main research areas of mine. Not very much familiar with your term graviton symmetry. So graviton
I
is
think this is
something from
something
particle
related to
physics.
string theory. Yeah,
Yes,
yeah.
so graviton, I really am not aware of this. I know that graviton, but I am not aware of the graviton symmetry. Sorry.
Right. Next question coming up from Raghav is that, ma'am, why dark energy is not detectable?
Dark energy is not detectable. That statement is not truly correct. You have evidences where the impact of dark energy is uh, happening. So we are still there to find out the uh, exact thing why where the dark energy lies, and in what respect the dark energy should be taken into account to deliver the theory better. So you have the evidence that dark energy is there, but not in a regular fashion or in a straight away mode. You have the impact of that, and from that we are trying to give some essence or give some aspect of dark energy in the theory.
That's fine.
And still this area is still to explore, so you can go ahead with that, because we have these days very observational data coming regularly from the GWs, and that bow data we are having, desi 2 we are having, CMB data we are having. So from that you can use your insights about this alternative gravity, and there you can check how the dark energy or dark matter concept needs to be taken into account.
Okay. When we are talking, Dr. Bhashati, about the smooth and non-smooth manifold, you remember? So what he is telling
Hmm.
is that from non-smooth manifold, I mean that one which has rough and sharp corners. I'm not exactly sure if it is true that we can do all calculus on that manifold or not. I think what he is trying to say is that in general, in general relativity, we say that we assume space-time to be a smooth manifold. So I think the question is
that
that can,
that
ah,
concept is yours. That smoothness is nothing to do with that rough thing or like that. That English literature term is a very tricky there, but if you just think about the rough surface and about those things, that is that gravity can explain. But your term is not very true in this respect. Yes.
we have got another question from NVPYOTR. What about phase transitions in a large statistical cosmological model? Could that explain dark matter?
It can be. It can be. The research is still going on, so it can explain dark matter. That can be.
Okay. Next question from Gurnur Singh. Why a freely falling charge does not radiate in its own frame?
Freely falling charge doesn't radiate in its own frame. What do you exactly mean by doesn't radiate in its own frame? Can Shona
I
give some
also,
insights?
yeah, I
I
also am
am
clueless.
not. I am very confused about this question.
Yeah, I would explain. I would, request the subscriber to just retype your question in a better way. Okay,
Yes.
we got a
Or maybe
question.
if they type it after the podcast, I can have a
Podcast you
look
can
and
you can answer,
I
right?
can just answer there. Yeah. But
The
this
next,
question is a bit confusing. That is the thing.
yeah, yeah. Okay, next
Hmm.
question we have got is uh, for four dimensions, there are uncountably many different smooth manifolds made from the same 4D topological manifold. What leads to the structure we use in general relativity? I am also not sure. Can you think of this, Dr. Bashir? I mean to say, I'm not very
For
clear.
four dimensions, there are uncountably many different smooth manifold. First statement is correct. That can be made from the 4D topological manifold. What leads to the structure? What structure exactly you are talking about? What leads to the structure we use in that structure is same for all the domain. The structure is same. Why do you think that the structure will be different? The field equations will remain same to account for the dynamics or the space-time thing. Why the structure will be different? The GR structure is same for all the things. If you go for a 4D topological manifold, if you go beyond that, that doesn't change the structure of the GR. That will remain same.
There is another question from Raghavan Manchanda. I am sure you will be very happy to answer. Ma'am, what is quantum gravity?
So truly, I was just speaking about this quantum gravity with Shounak before this podcast. That quantum gravity domain, I am very much confused about, and even the researchers in this domain are literally confused because quantum gravity is such a domain of research which needs to be cultivated or which needs to be explored till date or in the future aspects to account for the observations. So I really am not a quantum gravity person to answer your question.
No, but I think, Doctor, what he is asking, if you have the permission, I can answer. Quantum gravity
Yes.
is basically another way of approaching gravity where we are trying to quantify gravity in terms of quantum mechanics. Instead, that gravity is considered to be
See,
something like
if you
smooth.
just say that, if you just put it in that way, so quantum gravity it's also is a kind of extension of GR, right? So when we are going beyond GR, where we are seeing that GR is failing, when we are dealing with the quantum realm, when we are going to a subatomic level, there the GR, the usual GR fails, the classical GR fails, and there arises quantum GR. That I have already explained. But what exactly I thought of the question as that what are the research areas or what are the scopes of quantum jet, that I am not aware. But quantum, the essence of quantum gravity, I have already spoken into my
Yeah,
slides.
yeah.
That
I think that what he's asking that overall, what do you mean by quantum gravity? That is just a generic
so
idea.
then
That's
you
it.
can just think of that GR plus quantum mechanics or quantum real.
The marriage between the very big and the very
Yes,
small. That's it.
yes.
Okay. Okay, got question coming up from Jim Ramumsky, is a very old subscriber from US. What math could describe inside a black hole?
What math? Thanks, Jim, for this question. See, in the when we are going deeper inside the black hole, there the GR fails to explain. So now we can go beyond GR, as I have already said. There are many formulations beyond GR. That is your FR gravity can explain that. Maybe if you just take the normal Schwarzschild space-time and incorporate some extra parameters into that, that probably will answer your question in that inside the black hole dynamics. Also, I have worked in the supermassive black hole domain, and I have worked with several modified gravities to account for the things happening inside the inside GR. So many things are happening inside black holes. So I have specifically worked in accretion phenomena. So accretion uh, coming out of the black hole, but not only that, you can think of any extra dimensional theory. ADD model is there. You have your Brown's decay theory is there to encounter the physics or the dynamics happening inside the black hole. So if you just put into in a small statement what is the math gives the physics of the inside the black hole physics inside the black hole, so the answer would be your modifications or alternative gravity theories. That can be Brown's decay theory, that can be Horn disk theory, that can be anything. But which model is specific for which black hole, that is a questionable thing. You have to just figure it out. You have to just do the trial and error method and check which model is fitting much better or which model is not fitting better. That is the thing.
Absolutely. Thank you for answering. Jim, you got the answer. I recently made a video on general relativity, general part. So I actually spoke about the Brandstick theory, including that scalar, so that the capital G is now, instead of a constant capital G, it will keep on varying from time to time in the
Yes,
space-time. Okay.
yes,
Yeah.
yes, yes.
Yeah. Okay. Aniruddha Roy has got a question. Ma'am, in regard to gravitational lensing, what is the motivation for considering models where the source is assumed to be at a finite distance, like a Gibbons-Werner or Ono-Isharara-Asada approaches?
Right now, I will not answer this question. That answer will take too much time to explain. But just if you give me a month, I will share my own work on this with Shounak, and he can just give it to their subscribers so that they have the essence of this. So currently, I am working in this domain.
Absolutely wonderful. So, Aniruddha, you need to wait, and once doctors' papers are published, I will put the link over the
I will
description of
share.
this
I will
podcast.
share. Definitely,
Yeah.
I will
Okay.
share.
Okay. Tell me the happy news is asking, is there a difference in gravity discovered by Newton and quantum gravity? Obviously, there is a huge difference.
Obviously, obviously. That is the
Okay.
whole topic of today's discussion.
Today's discussion. Yeah, I think he joined it. Okay. His Highness, a friend of mine from Canada, is asking Hawking radiation may be from light trapped in orbit or charge left over from its mass defect creation.
I will not be able to answer very clearly about this. Maybe the first one is correct, the light trapped in orbit, maybe, but I'm not working in. I am not this realm person.
Absolutely. So you need to understand that gravity and especially general relativity is such a deep and specialized subject that people specialize even in gravity in different areas.
Yes,
Somebody
yes, yes,
knowing.
yes. See, when we were learning gravity, so we thought that gravity is one, one whole theory which will encounter all the fundamentals physics. But when I came into the research part, I came to know that there are whole lot of branches in the GR. Even when I work in the modified jet, there are also many branches. Maybe I know few of them, few are left unanswered for me. I have to also explore all those areas.
Gravity is such a huge topic, even relativistic gravity, quantum gravity, gravity in black holes, gravity on the event
These
horizon.
are
These are
all
taken care.
all
Huh,
the base subjects. See, when
base
we
subjects,
were
right?
young, we used to think English, Bengali, physics, maths. These are the subjects. Then, when we
Huh,
came into bachelor's, physics were divided classical, quantum.
right,
There is a condensed matter physics. There were
right,
all
right.
branches. Again, when we were in ITM, we see that classical itself was also several branches,
Yeah,
and
it
now
branches out in several. Right,
yes,
right.
yes,
Very
yes.
difficult. Yeah. So Jim Ronsky is telling thanks. I mean to say he always thanks us, and thank you, Jim,
Thanks,
for the
Jim, for
five.
your for inspiring us as well.
Absolutely, and thank you for the $5 immediate payment as a thank you sticker. So thank you very much. Okay,
Thank you so
one
much.
question coming up from regular shots. For instance, R4 has exotic versions that are homeomorphic but not diffeomorphic to the standard R4. Given this, what determines the particular smooth structure assumed in general relativity?
Given that, what determines that, you have to inculcate that. So you can't just state in a one sentence or just in a one shot what determines. You have to explore that, and you have to first fix which background you are talking about, which exotic versions you are taking into account. Those will be different. If you just take pulsar, the mechanism or the theory underlying that will be different. If you are going to a supermassive black hole, that will encounter for a different theory. Again, if you are going to X-ray binaries, that will encounter a different theory. So there are exotic versions which are the different parts of that which you need to incorporate, or need to involve in different areas. These are the different exotic versions, and different theories are developed for encountering these things. So
Absolutely.
one, in a single shot or in a one theory, you cannot incorporate or you cannot involve or engage all the things together. So there are, you needs
Absolutely.
to separate out.
Absolutely. Yeah, I mean to say what you were asking the person, tell me the happy news. R4 topology, if you're talking about, considering what Dr. Basheth is telling, that you really cannot tell that I have taken an R4. So what does it happen? So
Yes.
these
What
are
does it?
all,
R4 has branches, right? R4 itself have branches. You need to
yeah,
specify first which branch you need to work on,
yeah.
or which
I
branch you
remember
are interested.
exactly. Yeah, I remember exactly. You might be knowing there's a famous professor called Professor Daksh Lohia. He is
Yes.
basically a student of Stephen Hawking. We had a very long conversation over telephone 2 years back from Cambridge University. His theory got published, and Stephen Hawking called him, and they had a conversation at Cambridge. So I asked a very silly question. Don't take me wrong. That I told that, sir, if you put a ball on a trampoline or on a bed sheet, then it is curved. So can we
Hmm.
determine the curvature? So he told me that,
Hmm.
Shounak, it is not that easy. You put a ball on a bed sheet and you use Einstein field equation to find out the curvature. It is not that. So there are a lot of
Because
conditions.
see, here when we are asking about, or we are when we are talking about that daily life or everyday kind of these kind of experiments, we are not going beyond speed of light, right? These are the normal velocity domains, so you cannot just think of that it is a thought experiment. You can just imagine how the curvature is happening, how the space time is getting curved. That you can thought that elevator thing that we were discussing, that was a kind of mind reading or imaginative, that can be the thing, that can be the you can just say it has a kind of analogy you can put, but that does not mean that that is the exact realistic or the
Absolutely.
mathematical
Yeah.
foundations that will give.
Right, right. So whenever we are talking of any topological domain, it is not that we just take. Don't take me wrong. I'm not criticizing your question. It's a very well framed question. But when we are taking of a topological surface, we just can't tell that this is a topological surface. So how do we do that? We have to get a lot of initial conditions,
Right,
density,
right,
energy, etc. Okay.
right.
Coming to the next question. Uh, just a second. Yeah. Also, can you explain the result of Penrose's singularity theorem? Is it a proof of its existence?
Yeah, it can be proved, but not in a podcast. It can be proved, but you have to sit with a pen and paper and you have to check that.
I think what he is asking is that is Penrose singularity theorem, it is a proof or really that singularity exists in a black hole? I think regular shots you're asking that.
Penrose's singularity theorem exists, of course it exists, but to encounter that, the physics, underlying physics, I am not pretty much sure about, because I don't work in this domain. But yeah, if you just sit with a pen and paper and work it out, it will, you can just see on your own, or you can just check on your own that this theorem validates.
Absolutely. I think Penrose's singularity theorem is theoretically proved,
Right.
but we've
Not
never seen
yes.
inside a black hole, so we don't
See,
know that.
we were not aware of the black hole, right? We were thinking that is also a theoretical thing. But now, as we have discovered or observed the black hole shadow or the gravitational waves that we are seeing, we can check, or we can just know that that theoretical thing is happening right now. So it is getting observed. Who knows, that
Absolutely.
theorem is getting observed in later future. That can be the
Sure,
thing.
absolutely, absolutely. Regular Shorts is saying yes. Sorry for all the poorly framed questions. Thank you. You don't
Not at
need to be
all.
sorry.
Not at
All the
all.
questions are very
Thank you for
relevant.
the
Yeah.
lovely questions.
Okay. One question coming up is that what is Lie derivative in general relativity and what its uses? I mean to say why Lie derivative is used.
See, to encounter the curvature, the Lie derivative is uses. One of that is that covariant derivative that I have already talked about in the podcast. If you have missed, just go into the prior slides, or I'll just share the slides with Shounak if you wish, so you can have a look at it. It is a one kind of a Lie derivative. There are few.
Right. So I think, Dr. Bhashati, thanks a lot. We don't have any further questions coming. We are almost
Thank
one
you.
hour 40 minutes. I know you have a lot of problems in the personal
No, no,
life and you
it's
are not
okay. It's
keeping
okay.
well. But thank you very much. And okay, one question coming up. Just let us take it. Ma'am, how is the ISRO X-ray polarimetry
Polarimetry
satellite
satellite study black hole.
study black hole?
I don't know their mechanisms. I don't know their mechanisms.
Next question from Aniruddha. Ma'am, can you please explain the difference between a coordinate singularity and a physical singularity? Also, have we absolutely ruled out the possibility of an eternally collapsing object as an alternate? Oh, I mean, I think as an alternative, I think.
Uh, Alternative theory, I think. That needs a rigorous discussion. I don't think in a single statement or single line I can describe this. If Shaunak permits, maybe in some other podcast we will be discussing in these areas. If you just point it out, I'll just
Sure.
figure it out
But
difference
will it be
and
possible to just, in a few lines, overall an
not. A,
intuitive understanding?
can you just show
Yeah.
the question once again?
Yeah. This is the question.
As I was saying, that if you are, if we need to explain this difference between coordinate singularity and physical singularity, I have to write down the equations, and I don't have the pen and paper or any board work to, at least if I just draw some points and write it down, then it will be very easier to understand what is the difference. but without that explaining is very difficult. In a statement it is very difficult.
I wholeheartedly understand it is a statement, it is difficult. So that's Raghav is telling, please answer my question. Raghav, I think multiple times doctor has answered what is quantum gravity. So you can just go back. And thank you,
If
doctors.
not, then you can just put your questions on the podcast, on the link that Shonak will be sharing in the YouTube. Maybe I'll just have a look at it, and then I'll give some references, because as I have told that I'm not able to draw, or I am not able to describe in a boardwork framework. So I'll be able to give you some references so that you can be aware of these facts, and you will be have a better understanding of these conceptual things. That will be helpful, I think.
Yeah, absolutely. Thank you, doctors. When would be the next live stream? Just subscribe to my channel and click on the bell icon. I think on
Yes.
the 29th, we will try to, a person from Spain working on alternative, I think, black hole shadow. He will be coming, or we will announce, it will be announced. Okay, my friend is giving a thumbs up for Miss Bhashwati. Okay, thank you from Canada.
Thank
Okay,
you.
so
Thank you.
thank you, doctor. I think you have enjoyed. Any
Thank you.
last minute message on the prospects of general relativity for young people who are willing to take up, and then we can end the podcast. Anything from your side?
So, i- yes, surely. First of all, do subscribe this channel, because Shonak has taken amazing initiative by putting such lovely podcast on his channel. So just stay tuned with his channel so that you can get live updates or the research works which are happening, or just in future aspects of the GR. You can have a get a little bit of glimpse or have a essence of that from this, from his different podcast. But as Shonak mentioned, that what are the different research areas which can be explored, or which you can go through in the near future, is constraining Hubble parameter, Hubble tension, or that Hubble constant. That is a very good research area in cosmology, which are already many people are working, but there are many parts to be explored further. That is one thing. And modified gravity has enormous future, because many observations still not explained theoretically, and you can just get a model, or just frame a different model or different framework to encounter those observational aspects, and that will be a very fascinating theory in the near future. So these two, I'm saying in a two statement, but these has also several branches which you need to go through. One cannot go through all the branches, but you have to convince yourself first which domain you really appreciate to work, which you really enjoy working. So you have to choose first that, and then just go through the statistics or go through the literature survey, so that you can have a glimpse what already have been done and what more can be done. Because in every research work, people have already mentioned that what are the future things that can be done from that. So if you are giving a theory, they are already mentioned what are the limitations, what are the things can be done. This is how the research progress. So you have to first identify which domain you really want to work, and which fascinates you. For me, astrophysics fascinated me, that is why I am here. But you have to first inspire yourself, or motivate yourself, or ask yourself first which part you really want to work in. But modified gravity theory and constraining Hubble parameter or Hubble constant has enormous futuristic research areas which needs to be explored.
So last question, doctor, is that means modified theories of gravity, whatever the researchers are going. Point number one is that we are extending Einstein's field equations to certain more
Many
domains.
people, there is a confusion. Many people thinks we need to just change the gravitational equation. That is not the thing. Gravitational equation is there, you just need to modify accordingly to encounter the observational aspects. Maybe, see, there is a written g mu nu plus lambda small g mu nu equals to that t mu nu thing. That lambda can be modified maybe. The GBU, the space time can be modified, but the wholehearted equation remains the same. You just need to play around with this to encounter the observational areas. So Einstein is still celebrated. Yeah,
Absolutely.
now
Einstein
come.
is still celebrated and very well said. I would like to quote Doctor that only we need to modify so that it fits with what we see through telescope. That's
because if you want to frame a totally different theory, then you have to go through the observational test. That will be a pretty much big hurdle rather than an alternative or modifications of gravity. That is a totally whole different domain. I don't think that will be too easy to forget Einstein and establish a whole lot of new theory. So better we need to modify him, or the theories he have already discovered. We can modify that and we can encounter the observational areas.
absolutely. Samik Mitra has got a quick question. Which modified gravity model do you think could possibly have a chance to survive more aptly to explain SMBH images of the
At this
EH?
point of time, this is very hard to state that which modified gravity theory model. AFR gravity is very well celebrated, but which AFR model is very quickly give you the most appropriate explanation of SMBH or EHT, that we really don't know at this point of time. The research is still going on, and you can also you cannot anyways you cannot say that this theory is the universal, this modification is the universal. You can just jumble up between different theories and have a comparative study so that you can check that this model is better than this model. You cannot state that this model is the only thing that will explain all the physics or all the underlying physics of SMBH or EHT. That is impossible.
Okay, yeah. So Aniruddha Roy is telling, thank you, madam. It was very informative and enlightening experience. Okay,
Thank you,
so
Anirudh, for your lovely question. I hope you all
Raghav,
have enjoyed.
absolutely.
Thank you,
Lot of
Raghav.
people were online, and I think it will be more because it is now already on YouTube on my channel. People can watch it. Raghav Manchanda is also thanking, thank you, madam, and yes, so that's it. So, Dr. Bashiti, just stay online for 1 minute. Don't get disconnected. Thank you, all the subscribers, for your questions. It was a very long, I know, but general relativity is such a very interesting subject that we can
Still,
carry
many
on
theory,
discussing.
many areas is still I have not explained, because if I want to talk about all the things, it will take a whole lot of day. That then it will not end. This is such a
Absolutely.
fascinating theory.
Absolutely. So, thank you, all dear subscribers. Please stay tuned to my channel. After this podcast, there will be more videos coming up on tensor calculus, differential geometry, which I keep on doing that. Also, I am planning to make, I have already made 2 videos on quantum field theory explaining the Feynman diagrams, which will be more coming in this part. And thank you, Dr. Bashati, for a wonderful podcast. Thank you very much. It was truly
Thank you,
enlightening.
Shounak, for this lovely platform you have made, and I think you are doing amazing job in this
Thank you.
channel, and it will be go on. It will go on.
Thank you. Thank you very much. Thank you,
Thank you.
subscribers. Doctor, just stay online for a minute. Thank you very much.